All right, here we go. I might have said for a lesson last unit, it's like, oh, this is when stuff gets real. It's like, yeah, we had a lesson that was like intense in terms of all the stuff that we were doing. But today is actually the beginning of the rest of the semester. Like, what we're about to learn today is important for the rest of the semester. What we learned in Unit 1, we bring one thing with us to today. Okay, one thing gets brought from Unit 1 into today, and then we honestly kind of forget about it once we move to the next class. So, let's see how you do. We were told in the first lesson, like, you're about to learn the math of change. Let's get into it. Like, let's start learning the math of change, and let's answer the question, what the heck is a derivative? All right. All right, well, if I give you two sets of numbers, 3 to 15 and 5 to 9, like, what's the change? Like, how do you find change? What would you say the change is with those sets of numbers? Go ahead and tell your neighbors. Yeah, a lot of people are like, don't we just like add 12 and don't we just add 4? It's like, yep, you're right. 12 and 4, that's the change. Now, I kind of just figured this out by like 3 plus 12 is 15, 5 plus 4 is 9, that's fine. But we know that we actually can subtract these two numbers. And that's actually how we find change between any two numbers. Think about like distances on a number line. If I have a distance of 15 and a distance of 3, if I subtract the distance of 3, what's left is the distance of 12. So a lot of you are familiar with like subtracting numbers to see like the change. Cool? Now, lots of things in this world change, okay? There's lots of things in this world that we could analyze, like how is that changing? And we could like get into that. We will, in the second semester, like talk about how real world things are changing. But until the second semester, we kind of just need to learn the basics. So what we are actually going to do is not talk about real world things changing, but rather just like graphs. I'm going to ask you, yo, how is this graph changing? All first semester, we're talking about graphs of functions and how are functions changing. You guys cool with that? I'm keeping it simple for you guys. Yeah, hopefully. Good. Well, the problem with like graphs is like we have not just like values, 3 and 15. There are like points associated with values. Like there's an x coordinate that gives you the y coordinate. There's an x coordinate, say 7, I'm just making this up, that gives you the y coordinate like 15. Okay? So if we have like this idea of a graph of a function with these points, these x, y's, let's see if our idea about change changes. Like we would say 3 to 15 is more change than 5 to 9. You know, plus 12 is bigger than plus 4. But if there was like two things that we're looking at the same time, an x and a y, would you still say 3 to 15 is more change? Well, let's see. I got the 1, 3, the 7, 15. And then over here, I now say, oh, I got the point 2, 5, 3, 9. Is there another way to kind of compare the change going on here where we incorporate, these x's as well as the y's? Go ahead, tell your neighbors. What do you think? Good. You guys are saying the correct word, the S word. You're like, well, like my y's go up by 12, but I go up by these 12 y's over the course of 6 x's because 7 minus 1 is 6. So up 12 y's over 6 x's. Here, we're going up 4y's, but over the course of 1x. So 9 minus 5, that's 4. Cool. 3 minus 2, that's 1. But how can I compare these? Like, well, you guys are thinking slope. We divide. And when we divide, we change these numbers instead of like amount of y's per amount of x, we change this into a rate, a unit rate. This is 2, or 2 over 1. This is 4, or 4 over 1. And I'd say, hey, this went up 4 y's per 1x. This went up 2 y's for 1x. Or we start thinking about and we start graphing like lines. And we said, oh, hey, this is steeper. The slope is steeper. And all we're using, guys, is the slope formula. And guess what? This entire lesson is about slope. Slopes, and it gets more complicated though. Slopes give us rates of change. Slopes tell us how many y's we change over how many x's. We get a y per x rate of change. And here is kind of what we're dealing with in this class. I have a function. There's some equation that gives me this graph. I picked a couple of points because they end up on whole numbers and they're nice to use, but I can pick any point I want. And I'm going to ask you like, hey, what's the change from here to here? And you could say, well, I started at this point 1, 3, and I ended up at this point 7, 15. If I connected, that's going to be a problem. I need to get to my stuff. Yeah. If I connected these points of the line, and I calculate the slope of this line, and I found that the slope of this line was, what was it, 2? What I can now say is like, hey, on average, my function is going up 2 y's per x from 1 to 7. And instead of like saying from 1 to 7, I'll just like use like interval notation. So I'm going to say like 2 y's per x from 1 to 7. Now, why do I have to say on average? Why can't I just say f of x is going up 2 y's per x from 1 to 7? Tell your neighbors, why do I have to say on average? Good, it's not actually going up at this rate, you know? It's going up faster. Oh, it's slowing down. It kind of stops. It starts going down. It doesn't go up the entire time. It flattens out, it goes up. So like the function's doing a lot of crazy stuff. But we can say, because we know these 2 points, that on average, if you were to go up 2 y's per x from 1 to 7, you would end up like 12 higher. You'd end up at 15. Okay? We did the same thing with 2, 5, and 3, 9. It might appear that it is going at the same rate, but it's not. Like you can see, it's going to be like being a little bit faster, a little bit slower. We found the slope of this line was 4. And having that slope value now gives us this statement that on average, my function went up 4 y's per x on the interval from 2 to 3. Okay, slopes are changed. Really simple, guys. Slopes tell us how quickly things are changing. You guys do the last one for me. Why don't you just find the slope, and then I'll give you the interpretation, because a lot of your interpretations will be a little probably different than what I would say. Go. Don't worry about the statement, just get the slope. Check your slopes with your friends. Yeah, some of us will need to like practice up on our slope formulas. If I have a visual, I usually don't like to use the slope formula. If I have a visual, I like to use my good old friend rise over run. Not to scale, but who cares? I'm going down 5. That means like I've decreased 5. That means my change is negative. We're cool with like change being negative. We're cool, and we haven't seen it yet, but like slopes can be negative. Your y's could decrease. Negative change is a decrease. Cool. So if you go down over 4, well, the slope is negative 5/4. Now, a lot of people will say, oh, you go down 5 y's over 4 x's. Well, I'm going to say we went down 5/4 of a y per 1x. That's just a little bit more comparable. Everything is in a y's per 1x rate. Okay? So this 5/4, my interpretation is on average, my function is going down. It's decreasing. It's going down on average 5/4 of a y per x on the interval 2 to 6. Okay? Downward sloping line, decrease overall on average. All right? So, slopes equal change. That's simple. Slopes equal change. If calculus is the math of change, then calculus is all about slopes. And it's true. Nothing fancy. It's just slopes. If I ask you for an average rate of change, I'm talking about the slope of the line that connects 2 distinct points on a function. Okay? So we are just finding the slope of the line that's connecting 2 points on the function. Even though you might see like, oh, the line goes through 3 points, we don't care. We're talking about these 2 distinct points. The slope of this line being 5/4 is telling us an average rate of change. Now I will use for shorthand AROC. AROC, average rate of change. Okay? Average rate of change, slope of the line that connects 2 points on a function. And I'm actually going to call that something else in a second, in a little bit, because I don't want to say, oh, find the slope of the line that connects the 2 points. It takes too long. So I'm going to change that up in a little bit, give you a little shorthand thing. All right. Now, like the first page of your homework, first 2 pages of your homework is literally like these questions. Find the average rate of change of this function over this interval. And I'm going to give you a function, okay, x squared. And I'm going to give you an interval. Understand that the intervals are x's, x interval from x equals 1 to x equals 4. You could visualize it if you want to. And you'd be like, oh, I got to find this slope of the line. Okay, well, go ahead, do it. What do you do? Tell your neighbors, what do you do? What do you do? Yeah, we're missing some stuff, We're missing some stuff. We have the equation of the graph. We weren't given the equation of the graph before. We were given the x's and the y's of points on the graph, but we weren't given an equation. Well, now it's like, yo, you're given the x's, you don't have the y's. A lot of times in this class, we won't be given everything. We'll have to find some stuff. Guys, you need to figure out what is the y coordinate here and what's the y coordinate here. Plug in the x's, okay? Some of us were quick to be like, oh yeah, just do that. Some of us were like, ooh, I'm not sure. Your first page of your homework is literally just plugging in x's and finding slope. Using the slope formula, guys. Remember the slope formula? Yeah. Yeah. Guess what? We're going to use that a lot today. All right, so I got the point 1, 1, because when I plug in 1 squared is 1. There's 1 point. If I plug in 4, I get 16. So there's my second point, 4, 16. Now I find the change in my y's over the change in my x's. We're just using the slope formula. Five. Now we can say what that means. On average, y equals x squared. Yeah, function notation, y equals, it's the same thing, right? Y equals x squared goes up 5 y's per x from 1 to 4. Cool? Yeah. No, Rashad, just keep it in your brain, okay, bud? All right. I'll write it down on the homework video, but if you don't write it down, it's fine. You guys good with this? Do you want another one, or do you think it's I got that. This is easy. You don't have to do this one, right? Okay, good. Because your first page of your homework is just average rate of change, average rate of change. But that's easy, right? And that was easy for mathematicians from way back in the day. Earliest mathematicians, they understood that. But what baffled mathematicians until the 1600s, when Newton discovered this, was the following question. Okay? Pause on your homework because this is where we get really into the hardest stuff. What baffled mathematicians until the 1600s was not what's the change over an interval, but what's the change right there. At this point, on this function, how quickly are things changing? Okay? People could understand the theory behind it. They could understand what they were trying to look for. But it took until Newton to then be able to figure out, oh, this is how we're going to find the number. Okay? So, guys, if slopes equal change, right? And I'm essentially asking, how quickly is the function changing at this 0.47? Would it make sense that it's okay, let's find the slope at that point? And I guess it's the slope of the line at that point. We don't see a line, but we know slopes equal change. Slopes come from lines. Do you guys think you could draw maybe a line that kind of fits, and maybe we can at least try to see oh, okay, I'm trying to find the slope of this line, which will probably tell me how quickly the function is decreasing. Go ahead, give it a shot. What would you think a line would look like at that point? Yeah, but what would it look like? Draw a line that, yeah, something like that, Rashard. I like that. What do you think? Yeah, I like that. Give it a shot. Yeah, I like what you did right there, McCraw. It looks like if I could turn this into a line, it would look like this. if I kept going, it's like this. Did any of you, and it's okay if you didn't, it's okay if you're like, yo, I have no clue. Did any of you think of like drawing something that just kind of touched the function right there and kind of like mimic things right there? Yeah, like that's kind of instinctually what we can think of. It's like, yo, that's like the slope right there. Great. You just drew what's called a tangent line. Okay? You just drew what's called a tangent line. Now, mathematicians understood from a long, long time ago that if we can find the slope of this tangent line, we could understand how quickly the function was changing. Okay? But it took until the 1600s for Newton to connect two things for it to actually happen. But everybody knew the theory about it. Now, why did people from way back in the day, like from early on in math, call it a tangent line? Because like a lot of math started with the Greeks. And in geometry, a lot of math started. You guys remember from your geometry class, like when you heard the word tangent line before? Like what's a tangent line in geometry? Tell your neighbors, see if you remember. If you don't remember, who cares? Yeah, so it's actually not unit circle. We actually were introduced with the concept of a tangent line as a line that just touched the circle once, right? We are going to use that, and people use that same terminology to describe this. Okay, so that's a tangent line from geometry with circles. But we're going to say a line that just touches a function at one point. It might pass through in multiple locations. That's okay. What we're concerning about is like, here's where we created the line from this point, and like that slope is what we're trying to find. All right, and actually, there was another line that dealt with circles. You guys remember what we call the line that passes through 2 points of a circle? If it stopped at the edges of the circle, we'd call it a chord. But if it kept passing through, there's a different word. Anybody? No. No. What? It's a secant line. Yeah, you might have seen below there, Delana, but that's okay. So a secant line is a line that goes through a circle twice. They actually decided, and we can go back a couple pages. Yo, an average rate of change of a function, slope a line that connects 2 points on a function. Gosh, that takes forever to say. We're going to say the slope of a secant. This is like summed up in the bottom of that page. So, average rate of change, slope of a secant. If we want to find the instantaneous change of a function, the change at a point, the change at an instant, not the average rate of change, but the instant rate of change, or the instantaneous rate of change, or what we will call IROC. We understand that the slope of something gives us a rate of change. The slope of this tangent line would give me the rate at which this function is changing at that point. Change at an instant. People knew, yo, we needed to find the slope of a tangent. They knew that from way back in the day. But it took until Newton to actually figure out a formulaic way to find the slope's value. Mathematicians have been working on it since like zero, okay? And they've been talking about this concept over and over and over and over again, and they started getting tired because it takes forever to say slope of a tangent. It takes forever to say instantaneous rate of change. And like, gosh, let's just come up with a different word to use so that we can just like talk about this. And when we say this word, it means slope of a tangent, which means instantaneous rate of change. And they're like, cool, call it a derivative. So guys, what the heck is a derivative? It's a slope of a tangent, which will tell you how quickly things are changing at an instant. This is semester 1 of calculus, derivatives. Derivatives are just slopes. Okay? Okay. I sum it up down here. But like, the problem for thousands of years is what the heck is the value? I want an answer. I want a number. You guys are giving me numbers for average rate of change, but how do I find that number? Well, you guys actually know a characteristic of this number, of this function at 4, 7. Tell your neighbors, what would be a characteristic of this slope value, numerical value? Tell them. Look at you guys. You guys like know about slopes. You're like, oh, that slope is negative. Oh, negative values tell us that things are decreasing. Okay, that's very good. You got. We're working towards getting there. Okay, and actually we're going to find a slope really quickly, but we're going to cheat a little bit because I'm going to use a calculator. Okay, now Newton, Isaac Newton, who discovered calculus, not when he was at Cambridge, but when he was at home. Do you know what happened? The bubonic plague was ravaging England. And all the professors was like, yo, students, get out of here. Go home, go back to your farmhouses, stay away from people, okay? Let's do some distance learning, okay? You know what Newton did during his distance learning? He discovered calculus amongst other things. What did you do during your distance learning opportunity? Yeah? Did you guys make any cool discoveries? Yeah? You really like dive into some content out there when you were on your Zoom classes? Yeah, no, you did not. But that's okay. Newton was a special person. All right? And Newton was like, all right, let's just start with a function, x cubed minus 2. This is what it looks like. And let's focus our attention on x equals 2. All right, so here's the point at x equals 2 right here. And he's like, guys, I want to find this slope. Okay? And what did he have at his disposal? A slope formula, just like you guys. But the problem with the slope formula is what? You got to have 2 points. And we got a problem here. I only got 1 point. I got the point 2. And what's this y coordinate here? Don't guess. You should know what it is by plugging it in. What's the y coordinate right here? 6. He's like, I can't plug in, 6 and 6 and 2 and 2 and get a slope. I get 0 over 0. It doesn't exist. But you guys have seen 0 over 0 before. So he's like, you know what? Let's not worry about maybe the slope right there. Okay? Let's maybe use 2 points kind of close to that location, maybe close to each other so that like the distance between them is like 0, but it's not 0, it's just like close to 0. So what did Newton think about using? What x values do you think Newton would like to use if he knew he needed 2 different points? Tell your neighbors. So some of you are like, yo, the limit. So good job. But I kind of want some values. I have a calculator, so let's use it. So some of you are like, yo, let's use 2.01 and let's use 1.99. And if you thought that, like, great. You kind of picked up what I wanted you to pick up from last unit, that the concept of a limit is very important. And the concept of a limit is what Newton also discovered. And he's like, hey, let's use a limit in a slope formula. Now I'm going to go ahead and do this because what Newton couldn't do, I can do. Yeah, right on my desk. He did not want to spend the time taking 2.01 and cube it and then subtract 2. He did not want to spend the time taking 1.99 and cubing it and subtracting 2. Okay? But I can, if you give me a second. There we go. Here's the calculator. And you know what? I'm going to just do it like all at once. Like I could spend the time doing 2.01 cubed minus 2 and find that y value. But like I'm just going to put everything in a fraction. Alpha F1. Sorry, nope, quit. Alpha F1. Here we go. So I'm going to put this as my y2. This is my y1 all at once. So away we go. 2.01 cubed minus 2 minus 1.99 cubed minus 2 over 2.01 minus 1.99. Newton thought it's like, if only we could do this, we could have some magical thing that hasn't been created yet, find our value. And I get 12.0001. Now, are we comfortable with using just those 2 points? I mean, yes, but wouldn't we like to make sure, I think this looks like it's 12. Wouldn't we like to make sure it's 12? How can I make sure, like, the slope's going to get closer and closer to 12? Tell your neighbors. What would you do? No. Yo, use 2.001. Anybody think about just like getting closer to the point? Hopefully. If not, whatever. No big deal. If you said, yo, why don't we just get closer? And if I found this, and like this is why calculators are great, because you can do complex calculations very quickly. Oh, yeah, I got even closer to 12. What we are discovering using our calculator, combining our knowledge of a limit, our limit is how we're thinking about using this value and this value. Combining our knowledge about limits with a slope formula, we are getting our first tangent slope. The tangent slope to x cubed minus 2 at 2 is 12. That means this is how quickly that function's like at x equals 2, f of x is going up 12 y's per x. That's what we just found. At a location, how quickly the function's changing. Did you know your calculator has like a derivative button? You've never seen it before. But your calculator actually has a derivative button. If you go to math and you go down, you've never done this before. Just n deriv. This is like, yo, hey, I'll take a derivative for you. I will find the slope of the tangent. You're not familiar with this notation, but you will be next class. You can plug in, hey, calculator, tell me the derivative, the slope of the tangent of x cubed minus 2 at 2. we expect to see the number 12, right? Because it's like, yo, if I use points closer and closer to, eventually my calculator is going to stop rounding and it's going to give me 12. Well, I press enter, and guess what my calculator gives me? Not 12 on the dot, 12.000001. What's that mean? Your calculator actually did what we just did. This is how your calculator finds a derivative. It just uses slope. It's nothing magical. It actually uses the slope of 2 points very close to each other. So your calculator actually does not use what you are about to use for the rest of the semester, what Newton discovered, okay, which we're about to learn, because Newton couldn't do this. Newton was stuck at this spot right here where he's like, I need to find the slope. I need to use this concept of a limit and combine it with the slope formula. And that's going to be my approach. And Newton made it happen. Newton took his friend the limit and took his friend the slope formula. He was the matchmaker. They got married. They had a baby. And they called it a derivative. So congrats, Newton. Newton is like the original mathematical matchmaker. Okay? Newton understood, yo, we need to combine a limit with a slope formula. But he couldn't get 12. All right, but we're going to hold on to that number 12 because we found it. Our calculator found it, cheating. But we got to figure out how to get this number 12 the way Newton got it. Okay? So Newton had to start somewhere. He didn't have a calculator, but he knew he had to combine limits and slope formulas. And he's like, all right, well, with any problem solving, sometimes what we got to do is like use pictures. So he's like, let's just go graphical. Let me just like see if I can approach this a different way. So he started doing the following. He started taking functions like this x cubed minus 2. And he's like, you know what? I understand that the slope at points will tell me how quickly the function is changing. All right? Let me just plot these tangent slope values on another graph. Cool? And he didn't know the value of this number, but he knew a characteristic of that slope. Tell your neighbors, what's a characteristic of that slope? It's positive. Very good. So he thought, okay, if my slopes are positive, I'm going to plot a positive y value for this new graph, this tangent slope values graph. And he's like, okay, positive y value above -2, where like this is below -2, you know what I'm saying? Like that positive slope I just plot. And then he's like, let's keep going. At -1, this would be my tangent slope. It would give me the rate of change. Now, what's a characteristic about that slope? He didn't know the number, but he kind of knew a characteristic. It's positive, but compare it to the last one. Very, very good. We know that like shallower lines have smaller slope values. So if we had a number, this would be like 8, and this would be like 2 or something like that. So this is like a smaller positive. So I plot a smaller positive. He realized, oh, if my slope is like horizontal, if the line is horizontal, what's the slope of a horizontal line? You guys know that? 0. Okay? 0. There's no change of the y's. They're not going up or down at all. So he said over 0, I'm plotting 0. Okay, you do the last two. Okay? He's like, this is a tiny positive. This is a bigger positive. So he's like, all right, tiny positive, bigger positive. Now you guys see this. Looks like man, I really want to connect these points. It's always good to like check before you just start connecting things all willy-nilly, guys. So please, for our sakes here, go at the -1.5 and -0.5. Go at the halves and make sure like the slopes fit in between these points. Go ahead and just double check that for me. Do they fit? And then if they do, put your phone away or you're going to be tempted to look at it. Okay. And if they do, then we could be like, oh yeah, this makes sense. So like, imagine there was a point here, a point here, a point here, and a point here. Okay? Does it fit? Yeah, this one is a little bit less than this one, but more than this one. This one is a little bit less than this one, but more than 0. So they fit, and we could keep going with more and more points, and we plot more and more slopes, and then we realize, yo, my tangent slopes make a graph. Cool. And the graph is actually supposed to be a U, not a V. If you make a V, that's okay. Just know it's supposed to be a U. And Newton's like, wow, that's cool. Maybe all tangent slope graphs are U's. So he's like, let's look at another one. Here, we're going to change up the function a little bit, make it x squared minus 2. Okay. Take 1, 2, 3, 4, 5 points, sketch like the slopes, understand the characteristic about said slopes, and then plot those slope values where the positive slopes go like above the point, the negative slopes go below the point. Will this graph's slopes create a U, or will it be different? Good, Scott. You gotta try. Gotta try. Like what we did, you've already done this. Cree, you're on top of it. Everybody make sure you understand what Cree's doing. Perfect, Hedrick. Don't worry, we'll get it. You're on top of it, Richter. McGraw, right on it. Perfect. Okay? Look at McGraw. Look at Carr. You guys are all over this. Nice. Excellent. Love it. All there. We good? Yes. Good. It doesn't have to be perfect, but what I wanted you to see is that, like, yo, this slope is very negative. This slope is less negative. This slope is 0. This slope is a little bit positive. This slope is very positive. And then you realize, yo, they're not all U's. Okay. Some of them are like lines. I don't want to do this one. Whatever. We'll stop there. Okay. And he kept going. How about with this today? He kept going. He looked at different graphs and he looked at their slope graphs. And he realized, yo, every single function had a unique slope graph. Okay? Like this function had a different one to this function. This one was different. Maybe some were used, but they were located in different spots. So he's like, yo, that's cool because I know graphs have what? What do graphs have that helps like create them? Points. Where do the points come from? Like inputting values into what? An equation. Guys, Newton, he still has the limit and the slope formula, the love connection in his head. But he's like, here's another thing that's cool. Functions have tangent slope equations. And here's what Newton said. He said, yo, if I had an equation, I could theoretically plug in 2. And when I plug in 2, I'm going to get this y value. And that y value will give me this slope. So Newton's like, and we already did this with x cubed minus 2. Newton's like, I'm going to find an equation. I'm going to plug 2 into it, and I'm going to get this number, which we know is going to be 12. Right? Because that slope's 12. We used our calculator. We cheated. Okay? Newton's got to find that 12, though. But his approach is like, I got to find this equation. The idea that there were these equations that had y values that produced slopes were so important to Newton. He's like, I got to call these something special. And since they were all unique to its original equation, they were all different, they're related to f, he called them the f prime. Now that's not a 1, that's a prime. And f prime is unique to its f. All of these f prime equations are different if you have different f's. And like, he's like, this is good. The f prime y values are going to give me slopes of f. The y value on this graph is going to be 12. That's going to give me this slope of 12. But Newton didn't know that was 12. He's just like, I got to find that y value. All right? So he's like, okay, now my goal is to find an equation, not to really pay attention to things. So he's like, I need to find the equation. He still had in the back of his head, like, what's the key to this whole thing? The key to the whole thing is the marriage of the limits and the slope formula. But he needs to marry these in such a way to create something that would then find equations. Okay, cool. Here's how he did it. Now, imagine you came up with this. He took a random function at a random point x. He's like, oh, this could represent any function. X cubed minus 2, x squared minus 7, whatever. X cubed plus x squared, who cares? He's like, at that point, we have a function value, x, f of x. Yeah, it's weird, but that's what we're going to go with. And then he's like, let's take another point that is h distance away. So like if I add an h distance, I get to this point, x plus h. And he's like, well, if this is x plus h, and I plug it into this like generic random function, I got f of x plus h. And he's got now 2 points, which again are not using numbers, which freaks you guys out. But like this is what he had to work with because he didn't have a calculator. You got x plus h, f of x plus h, and he's got this point x, f of x. And he's like, listen, let me just use this as y2, x2. Let me use this as y1, x1. And I'm gonna plug it in there because that's all I got. I know I have to marry limits and slopes together. Let's see how we can do it. So he's like, all right, well, I got f of x plus h minus f of x. So we call that's y2 minus y1. All right? And that's divided by x plus h minus f. Now, what do you guys realize in the denominator there? Yeah, the x's are gone, right? Like, let's think about this. What is x2 minus x1? It's the distance between the 2 points. It's x distance. What is the distance between these 2 points? H, right? So like the x's go away, and you're just left with h. And he's like, great. I now have a very, very, very generic formula for slope of 2 points, h distance from each other. All right? And then he thought to himself, well, like, what's the key? We have to have 2 different points, but we can move them really close together. We could take this second point, and I can move this second point to be infinitely close I'm going to use a limit. And he's like, okay, I'm going to use a limit now. And he's like, I'm going to take the limits of this formula. But what goes here? Well, he's like, I'm going to take these 2 points and I'm going to make them really close together. I'm going to try to shrink this H. What goes here? This always stumps students. Now, we're always used to X approaching things, but now, what's happening to H as these 2 points get closer and closer and closer together? No, what? H is approaching 0. Different. You guys are all used to X's, so this is new. But they're like, yo, take the 2 points and have their distance approach 0, and we now have the marriage of limits and slopes. We now have a formula that's going to give us the slope of 2 points like infinitely close together, or we have the formula for a slope of a tangent. Newton was like, yo, since I just did this for any function at any location, I bet you I can use this fancy-wancy formula that I created that marries the limit and the slope formula. Here's the limit. Here's the slope formula. It doesn't look like it, but it is. 2 points are h distance away. I bet you that's how I'm going to get those f prime equations that I could hopefully plug into or any other value into and get values of slopes or get 12. Sweet. Let's try it out. Now, we know what we should end up with, kind of. Like, this is a U. What kind of equation is a U? Quadratic, some sort of x squared, right? So guess what? We kind of know what we're going to be, like some sort of x squared. But Newton's like, I bet you this magical formula will give me the exact formula, not just guessing. So he's like, okay, away we go. I've married limits and slopes. I have a very generic formula for the slope of any function at any point. I think this is going to give me equations. He's like, let's try to plug this into that. And it's like, well, we can't really plug in that both places. I could plug that in for f, but I need somehow f of x plus h. This is where you guys just stop. Just stop writing. Just pay attention. Like, you won't have to do this process. What's magical about this formula is that he then plugged in like more theoretical generic forms of equations. He created rules, but like before he created the rules, he tried it out on functions like this. What I'm telling you is that you won't have to do what I'm about to do. Just pay attention to the creation of this equation. Okay, we are about to find this f prime equation, this tangent slope graph, its equation. All right, here we go. So this becomes x plus h cubed minus 2. Don't copy this down again. It's a waste of your time. This is that. And I'm going to plug it in. And let's see what happens. And you're like, great, Newton. Are you sure you're going to find an equation? Newton's like, I got it. Just wait. Just hold on. It's gonna happen. He's like, oh, let me just simplify some stuff. You know, let me cube x plus h. I get it. X cubed, I don't know if you guys know how to cube things, but this is what it is. X cubed plus 3x squared h plus 3xh squared plus h cubed. That's x plus h cubed. You just got rid of the parentheses. So then he's got this minus 2. Let's distribute the negative. That's a minus x cubed, and this is a plus 2. And again, you're probably thinking, yo, Newton, are you sure you're going to get an equation? He's like, yep, I'm going to get an equation. This is going to be the way I'm going to find that value 12. Just wait and see. And then he realized, okay, this x cubed and that x cubed, that's gone. This negative 2, that positive 2, that's gone. And he realized that the remaining terms have an h in it. He's like, well, I can factor out the h. And then he realized, yo, if I want to plug, we'll find the limit as h approaches 0. I want to plug in 0. I couldn't plug in 0 or else I'd got 0 over 0. But if I plug in something close to 0, this number would cancel with this number. This would turn into 0. This would turn into a 0, which means this would be gone and this would be gone. And the limit's value would be 3x squared. And Newton's like, Eureka, I have done it. I just found f prime is 3x squared for x cubed minus 2. What did you just find? Go back in your notes and be like, oh, you just found this. Well, no, like fill in. There's a blank I left somewhere in the notes. Fill it in. What did he just find? There's a blank somewhere that we left that you need to like, oh yeah, you just found this. That's it, Haley. Make sure you got the right one. Yeah. What did he do? What did he find? What did we just find? Keep going. Nope, not here. Not here. Keep going. Keep going. Keep going. Oh! He found for x cubed minus 2 that this graph's equation is 3x squared. And Newton's like, sweet, I can find any tangent slope to x cubed minus 2 that I want like that. For example, at 2, Newton found the number that we found using a calculator like that. What did he get? How did he get 12? We used the calculator to get 12. How did he get 12? Tell your neighbors, this is important. Yo, Newton's like, if you have this equation, then all of the y values of this equation gives you slopes for f. You can just plug in, not just 2, but any x value you want. I plug in 2, I get 12. That slope is 12. All right, well, let's fill out some more slopes, guys. At 1, what is the slope? We know it's positive, but positive what? At 1, we didn't get this slope. We could go back and use our calculator to like check. What did he get? What is the y value here? 3. If you plug in 1 into this, you get 3. This slope is 3. We think this is 0. Is it 0? Great. What about at negative 1? What about at negative 1? Yeah, if you plug in negative 1, you also get 3. What about, and this is where we can go back and catch up with their notes, what about the instantaneous rate of change of x cubed minus 2 at x equals negative a half? Whoa, Mr. Messner seemed to have gotten a lot harder. No, it didn't. This just means slope of tangent. If you had a calculator, you could just use the derivative button, which just uses the slope formula, and you'd use like 0.49999 and 0.500001. Sure, but not how Newton did it. Newton was like, yo, if you know the tangent slope generating equation, which he found by marrying the slope formula and a limit together, you just plug in negative a half into that. So go ahead and do that. What's the slope of x cubed minus 2 at negative a half? Three-fourths. X cubed minus 2 at negative a half. Its slope, 3/4. That's how quickly it's changing. We could say at x equals negative a half, y equals x cubed minus 2 is going up 3/4 of a y per x. Just like incredible information just from this. Newton changed the whole game, okay? You guys in the past were asked like, hey, examine x cubed minus 2. What would you do? You would look at x cubed minus 2. You would do stuff to x cubed minus 2. Newton discovered, yo, you want to look at x cubed minus 2? Who cares about x cubed minus 2? Look at f prime, 3x squared. All right, now, scroll down. Newton's like, I got to make sure this works. Let's look at x squared minus 2. Okay? Now, Newton / me, he took x squared minus 2. He plugged it into his magical formula that married the limit and the slope formula together, and he got that f prime is 2x. Now, this is important. 3x squared is only the f prime for x cubed minus 2. They're all unique, these f prime graphs. Go back up if you want. I know we're flipping back and forth, and you don't have to just pay attention. Remember how this f prime graph was different than the first one? Because this graph looks different, so its slopes are going to be different. Well, guys, 2x is the equation of this. But what's important, especially because we get a line, is that, like, you guys think of 2x as being a line and it has a slope 2. No, don't think about it. This f prime, the y values of f prime tell us the slopes of f. So, what are the y values at 2, at 1, at 0, at -1, and at -2? Go, find the y values here, 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 and here. Right? Easy. This is 4, this is 2, this is 0, this is -2, this is -4. Guess what? This slope is 4. This slope is 2. This slope is 0. This slope is -2. This slope is -4. The y values give you the slopes. Brilliant. Brilliant. He changed the way that math was kind of thought about and analysis of functions was. He's like, yo, change the question. And now we're going to do something great. We are going to write our first tangent line equation. And we're going to see it. And we're going to leave class feeling good about ourselves. We've been sketching these tangent lines, but they have equations too. And we're going to use the point slope form of an equation. Okay? Y minus y1 equals m times x minus x. And since it's a tangent line equation, the slope is the tangent slope. Now, where do we get tangent slopes from? Tell your neighbors. This is like the key to this lesson and the key to the rest of the semester. Where did Newton get tangent slopes from? That's really what I should be asking. Where did Newton get tangent slopes from? F prime equation. F prime y values. F prime equations produce F prime y values. F prime y values are slopes of tangents to F. Okay. This is just a point on F, the original equation. Okay. So let's go to x squared minus 2. Oh, stop doing that. Okay. Newton used the magical formula. He plugged x squared minus 2 into his slope slash limit combination formula. It gave the equation f prime is 2x. First, remind me slash confirm, what is the slope of f at x equals -1? Or what is the instantaneous rate of change of f at x equals 1? Or what is the derivative of f at x equals -1? Tell your neighbors. This is important. Very important. It's like so simple, but it's like important. Very good. Slopes of f come from y values of f prime. Newton's a genius. Thank you, bubonic plague, for sending him home so he could discover calculus. Not sure if that's too soon. Is it too soon? I don't know. We'll figure it out. All right. Okay. So we plug in -1 and I get -2. Guys, that's an M. You might see like 2 and you're like, oh, that's a line. The slope is 2. It's like, no, 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 no. The y values of the line give you the slopes of f. Okay. So the slope is -2. So if I'm trying to fill out an equation, I got y minus y1 equals, there's f, x minus x1. Okay. We're talking about x equals -1, so that goes right there. What goes right there? Figure it out with your neighbors. Go. Oh, horrible example. Darn it, horrible example, but it's fine. Never mind, I changed my mind. I'm going to change this to x squared minus, I don't like that either. I'm going to change this to x squared plus 2, okay? But it turns out that doesn't change that. I told you they're all unique, but like x squared plus any numbers, they're all going to be 2x, okay? So I changed it to x squared plus 2 because I don't want to repeat numbers, okay? The slope is still good because this is still the equation. That's still the magic equation. Okay, since this is x squared plus 2, this is still -1. What goes there? What goes there? 3. Tell your friends where you got 3 from if you got 3 at your table. We go back into the original equation to find the point, the y coordinate of the point on the function. So if you think about x squared plus 2, here's x squared plus 2. I need this point so that I can have my tangent equation, okay? So I plug in -1 into f, and I get 3. I wanted to get different numbers so you guys don't get confused. It's important to get different numbers when teaching. Okay? So now I'm going to get this equation, y minus 3 equals -2, x plus 1. Guys, you do not have to solve for y and put things in y equals mx plus b form. Just stop right here. If anything, if you were to graph, you can easily graph by adding the 3 over and leave it like this. We don't care about y-intercepts of tangent line equations yet all. So let's see our beautiful work in living somewhat color, black and white. I got x squared plus 2, this equation, which I think has a tangent line -2, times x plus 1 plus 3. Big money, big whammy, no whammies, no whammies. Here's x squared plus 2, and there is my first tangent line equation. Isn't that cool? For yours, not that much work. It's so much work that Newton did. Newton did the hard work. You guys will find that given a function, it is so easy to find its tangent slope generating function. Quick. And you will be able to find tangent slopes quickly and easily because Newton did all the work for you. So thanks, Newton, on the way out. Make sure the chairs are all back. I think that counts. I think we did it.